Hi, I'm Dr. Paul Pienta, and these are the e-lecture videos for general chemistry. This is the first video. Let me give you a little introduction. The videos are pretty straightforward, I think. In the top left corner up here, there is, well, me. Down in the bottom left, you'll see my calculator. So as I'm doing calculations and entering them, you can see those exactly how I'm entering them. You can hopefully do the same. And then the main area of the video out here is going to be my lecture notes. You can actually read my lecture notes as I'm lecturing from them. And I would recommend, highly recommend, that you take your own lecture notes while you watch these videos, just like you would do if sitting in a classroom. Also, these lecture notes, I stick very closely to the textbook. I'll use the same figures from the text, the same tables, and so hopefully it'll be all consistent for you. Okay, let's jump right in. A little history of the chemistry. History of chemistry goes back thousands of years. The book mentions about 2,500 or so. See, humans for all this time we're trying to manipulate our environment, trying to change things, trying to use them as tools and whatever. I mean, whether it's fire or cooking something or making dyes, weapons, that kind of thing, pottery. It's all chemistry. And so in one way or another, by trying to manipulate things and control things, we have been doing chemistry. Might not have realized it, but we have. Soaps, magic potions, if you're trying to make an elixir or something, well, you're trying to be a chemist, okay? The Greeks actually had their 4 basic elements that they thought everything was made out of, and that was earth, water, air, and fire. And, you know, if you think about it, everything in existence is either matter or energy. Energy kind of correlates with fire, right? There's light and there's heat coming off, that's energy. And then matter correlates with the idea of earth, water, and air. Especially if you think about it, earth, water, air, that's solid, liquid, and gas, the phases of matter. And so, you know, they weren't too far off actually. It was a good start. Alchemists saw that you could change things and they would see the log, when you burn it, it changes to ash, that kind of idea. And so they spent a lot of time trying to turn other base metals like iron or copper or whatever into gold. Well, that'd be good if you could try to do that, or if you could actually do it. You can't, unfortunately, and we'll talk about why that is impossible. The book has this really cool little picture of an alchemist's lab, I believe. You've got some furnaces, some things going up in smoke back here. Looks like over here you've got some distillation type of equipment. Someone's turning, mixing something here. I'm not sure what this little pit is here. More distillation, perhaps, combustion chambers. I don't know what this is. It's got this pot in this circle. I don't know if that's fire or some kind of an herb or a plant. Kind of looks like something from Supernatural, if you ask me. Anyway, we've been doing laboratory type things, chemistry, for many, many years. Of course, modern labs don't look quite like that. Chemistry is often referred to as the central science, in the sense that it is really connected with all other branches of sciences, whether you're talking about astronomy, whether you're talking about polymer chemistry, maybe you're talking about biology, DNA, proteins, and lipids and such. Maybe you're going on to physics or the physical sciences or engineering. It's all comes back one way or another and is connected to and relies upon an understanding of chemistry. And so it really is a central science. And to understand any of those other sciences, you need to have at least a basic grasp of chemistry. Now, the precise definition of chemistry that the book uses is the study of the composition, the properties, and the interactions of matter. Or another way to put that, it's the study of matter and the changes that it undergoes. You could study just matter, but that might get a little boring after a while if it's just kind of sit there and doing nothing. It's the dynamics of it. It's the fact that it does react, it does change, that you can have an explosion, or you can digest your hamburger. All that's chemistry, and the changes are very important. Chemistry is also a science that has both observation and experimentation. We can observe things, and then we can take that into the lab and we can try experiments and see if we can make some kind of understanding of it. Now, all types of science rely on the scientific method, and so it's good to review what that exactly means. The scientific method is a systematic way of approaching an investigation of observations and curiosities in science and trying to understand them in a way that leads to reproducible conclusions and reproducible theories and laws. Alright, so it would start with some type of an observation, or as this book says, a curiosity perhaps, even if it wasn't just an observation. And the first thing we do is we form a hypothesis. that word, if you think about it, hypo meaning below or underneath, and thesis, so it's something that's below a thesis or below or not quite at a theory level. It's your first guess. It's an educated guess, but you look at it and you make your first reasonable sort of explanation of what it was that was happening. Some first predictions that your hypothesis could lead to. And then, well, we test it. We get in the lab if at all possible, and we see if our hypothesis holds water or not, as it were. And so we perform experiments. We make more observations, and then we compare that to our hypothesis. And the results, as it says here, are not consistent with the prediction. Well, then you have to go back and rethink your hypothesis. Maybe scrap it and make a whole new one. Maybe just tweak it a little bit. All those are very common. Very, very rarely would we get it exactly right on the very first hypothesis that we form. And so we go round and round and round until it starts becoming consistent. When we're pretty happy with it and we're not finding things that are not consistent, we're no longer finding those, then that's what this arrow here in the diagram says, the results are consistent with the prediction, then we contribute to the body of knowledge. So there's a chunk out there, we made the observation or the curiosity, we've explained it, and we seem to be pretty happy with our explanation. We don't really find things that go against it. And so now it's out there. It's out there for other people to take a look at. It's other people to do experiments with. Someone else might look at that hypothesis and say, yeah, but does it work over in my neck of the woods, right? Does it work with the molecules that I'm studying? Does it work in a giraffe as well as an elephant? That kind of a thing. And so they're going to look at it. They're going to do experiments, and they're going to make observations and see if it's still consistent. Of course, this back arrow over here says that further testing does not support the hypothesis. Now it's back to the drawing board again. Let's see if we can tweak it some more or make a new hypothesis, that sort of a thing. And so it's this repeated nature, it's this repeated cycling around and around, both with other people and without. And this, that process could go on for hundreds and hundreds of years. At some point, sometimes, a hypothesis becomes consistent with whatever observations, with whatever tests, and whoever is doing it. It's repeatable, the results, the predictions are good. Of course, we can never have 100% certainty, can we? It could be around for 500 years, and all it takes is one smart, clever little person to come along and say, look at this example, it does not support it, and we'd be back to the drawing board. But the longer that it's out there, the more people look at it, and if it is consistent, then we gain a great deal of confidence in that hypothesis. And at some point, it goes to the next level then. And that's what this last bit of this diagram is showing you. Let's look at the bottom first, because there's kind of two branches that it goes to. The bottom one says that much additional testing supports the hypothesis. So we're talking about further testing, further experiments, by lots of other people over many, many years. When it's really turning into a solid, well-supported hypothesis, then it becomes a theory. So a theory is a hypothesis that has withstood the test of time. It withstood the test of thousands of experimenters. All right, we have great confidence in it. That word theory is misused quite a bit nowadays. People use it actually to mean an opinion. Well, my theory about that is blah, 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 Well, no, that's your opinion. It's not your theory. Maybe it's your hypothesis. You might be able to say that, but theory is something very specific in science, and so please use that word correctly. The top one, it says much additional testing yields constant observations. So here we're not necessarily trying to explain it, but we're just making more and more and more observations. And as long as those are also consistent with the hypothesis, then those constant observations, as you see here, becomes a law. Again, the word law there is used in a very specific way, just like theory is down here. Here, a law is an observation that has withstood the test of time. I might make the observation that the apple falls down from the tree and hits the ground. It never falls sideways, it never goes up, right? It never breaks up into a million pieces on the way down. The apple simply falls down and hits the ground. And, well, is that observation true in Italy, Poland? Is it true in Australia? If there are trees on the moon, maybe we'll take a tree up there, I don't know, but would it be true on the moon? Does it fall down and hit the ground? What about on Mars? If the more and more observations, the more and more people that can make that observation, it invariably turns out to be the same. At some point, that observation becomes the law. So you have the law of gravity, for example. All right, so scientific method, make sure you use those terms correctly and understand them, not in the kind of the generic way, but the very precise scientific method way. All right, finally, in this one we're going to talk about the domains of chemistry, and there are three of them: the macroscopic, the microscopic, and the symbolic. Just the domains that we work in, that we think in, that we try to explain things in. So this picture illustrates it nicely. Here we got a picture. It's a picture of water, right? We got the liquid water, the ocean, or whatever this is down here. We got this big old iceberg floating in it. Well, that's liquid water. This is solid water. And then you got the clouds and the vapors up here. So that's gaseous water or vaporous water. So a big picture of water. This is the big world. This is the world that you and I live in. Macroscopic, kind of what we can observe with our own eyes, if you will. But if we can get a good enough microscope, if such a microscope even existed, that we could really see the molecules and the atoms of what's happening really on the small scale, that would be the microscopic domain. And so that gaseous water would look like actual individual water molecules with lots of space in between them. That solid ice would look like the same H2O molecules, but now they're structured, they're connected in a very systematic, repeatable, crystalline type structure. And then this liquid water, again, it looks different. You got all the water molecules, they're kind of swimming past each other, but they're not connected necessarily in a terribly organized way. Microscopic domain, very different than the macroscopic. Right? And finally, how do we actually represent it, the symbolic domain, right? How do we actually share and talk about it, predict things with it? We don't go around and draw icebergs all the time or try to draw the molecules in the way. No, we use the symbolic. So this is all water. Water is H2O. Well, this is H2O in the gas phase, H2O in the solid phase, H2O in the liquid phase. You tell any chemist H2O solid, they know exactly what that means, and they probably have this kind of a picture of the crystalline structure in their mind. And of course, the macroscopic picture they probably also are familiar with.